Dear students, I am Dr. Rajesh Sharma, and we have started with lecture 1. In lecture 1, we have discussed that what are the details of the syllabus for the experimental techniques in physics SPT-703. Now, in the second lecture, we would like to come to the scanning electron microscopy. And in short, I would just write it as SEM. So the first question that we would try to answer is why electron microscope is required. Second question which we would like to answer is optical versus electron microscope. What are the advantages of the electron microscope over the existing optical microscope that we have to discuss in detail. And after that, we would like to come to the instrument details of the scanning electron microscope. And finally, we would also explore what are the references in this case. So let's try to come one by one to these topics what we are talking about. And so before introducing these electron and the optical microscopes, I would like to come to one point that oftenly we come across the two terms. The one are the bulk materials. One type of the materials are bulk materials, and the second type of the materials we will come across, that is, these are the nanomaterials. No? So what would be the basic difference between the bulk material and the nanomaterial that we have to understand, and that will give us the answer that why the scanning electron microscope is important in order to have the images of different particles. In case of the bulk materials, the particle size is of the order of micrometer. So what will happen, that the particle size that would be of the order of micrometer, and in case of the nanoparticles, the particle size would be of the order of nanometer. So 1 micrometer, as you know, that 1 micrometer is equal to 10 raised power minus 6 meter, and 1 nanometer is equal to 10 raised power. So 1 nanometer is equal to 10 raised power minus 9 meters. So that is, if we would like to explore the particles whose size is of the order of nanometer or the micrometer, then we need to have an electron microscope. Of course, we can also have the study of the bulk particles or bulk materials with the help of the optical microscope. That we would also discuss in our next question, that how an optical microscope would not be better instead of an electron microscope, that we would like to discuss in this case. So what will happen, that if you would like to record the images of some specimen sample to explore the further details of the sample, then what you will do, you will go for the scanning electron microscope studies. So why do we need to image? So what I am writing here is to obtain images of the specimen. And specimen means that we are talking about the bulk or nanomaterials in this case. So now the second question which we have to answer is that we have started with this the optical versus electron microscope. What was the problem with the optical microscope, that we need to introduce the electron microscope? That would be our the next question which we would like to answer. So let's come to the second point which we would like to come here. So what we are going to do, that the second point, let's understand that how does an optical microscope works. So if you look into the details of the optical microscope, so you have an objective lens, and what you do, that you have a sample. This is lens and this is the sample, and then what you do, that the sample which is placed, so light will come through the microscope objective, and then it will be reflected back, and you can see the image of the sample which is there on the stage. So what you would have, if you have a small sample, then you can look at this sample with the help of the light which is coming from there. No? So if you look at the light is of the order of the electromagnetic radiations are having the wavelength from 400 nanometer to 700 nanometer. And I would like to introduce here what is Abbe's diffraction limit. No, Abbe's diffraction limit. No, this is an important parameter which will decide that why we need to have this the electron microscope. So what we would like to see here, that the optical resolution in the case of an optical microscope, that would be given by D is equal to 1.54 lambda over 2n sine of alpha. So this is the equation that was given by Abbe in 1873, and what he told, that what will happen, that the optical resolution of the microscope, the optical microscope, that will depend on the incident wavelength lambda, and that will depend on the n is the refractive index of the material, and alpha is the angle subtended by the microscope objective onto the surface of the sample. So what will happen here, that we would like to explore this point, that what this parameter it is. So the n sine of alpha would be equal to the numerical aperture. So what I'm writing here, so it is the numerical aperture. So what is the meaning of the numerical aperture? That this means that, okay, it is the light gathering ability of the microscope objective in this case, in case of the optical microscope. So what will happen, that your if you have very good objective which can focus the light, all the light which is coming from here to the specimen sample, so in that case what will happen, you would have the numerical aperture that would be equal to 1 in this case. So if you recall, then approximately the D that would be equal to lambda by 2. So what does it mean? That in this case the resolution of the optical microscope is lambda, which is the wavelength, divided by 2. So it would be, for example, if we are taking the wavelength, let's say it is 400 to 700 nanometer. If we are taking it like, let's say that we are taking it 400, the blue region, then the optical resolution will be like 200 nanometer. It would be like 200 nanometer. So this means that this is the limitation of the optical microscope. We cannot have the images of the samples which are smaller than the 200 nanometer. So if we have a sample whose particle size is, let us say, 100 nanometer or 150 nanometer, then the optical microscope is not a good alternative to measure that sample. So that's what we would like to see here. Okay, so this is the optical microscope. Why do we need to have an electron microscope instead of the optical microscope? So if we are able to understand this point, then what we are going to do, let me come to the second point here. So we are always focus on this point, that is the optical versus electron microscope. So what happens in case of the electron microscope? Let's see it. So in case of the electron microscope, if you look into the electron microscope, so what you would have, instead of having the visible radiations, so we see that, okay, what will happen, instead of having the visible radiations, here you would have the electron beam. So here you would have the electron beam, And this electron beam, what it will do, that it will be, when it will be incident onto the surface of the sample, so what will happen, that there will be the interaction of these incident electrons with the sample, which will result either into the backscattered electron. The electrons can go in the same path from where they came. Second possibility is that there may be the secondary electron emission, and there are another possibilities like the characteristic X-ray emission and brimstone emission. We are not right now considering these events. We will discuss these in our next lecture in detail. But only point is that the resolution, which was limited by lambda by 2 in that case, so it was lambda by 2 in that case. What will happen with the help of the electron microscope, when you have incident beam of the electrons hitting the target sample, you can make the lambda as small as possible. So for example, with the help of the lambda, if you the lambda is small, then what will happen, ultimately what will happen, lambda is small, so what will happen, that your d will be small. So you would have advantages of using this lambda. So how this second question is that how this lambda can be made small enough. So let's come to this point, that how to make this lambda small. So let's have a small expression, which is kinetic energy. As everybody knows that it is half mv square, and then if I would like to, what I will do, that I will multiplying and dividing with m, no? So it would be m v square, no? So it would be p square by 2m. So it implies that if you would like to, this is the energy, kinetic energy. So what it would be, that it would be p is equal to under root 2me. And you know that de Broglie, he emphasized that every material particle is associated with a wave, and the wavelength of that wave will be equal to h over p. It implies that it would be h over under root 2me. So what will happen, that if you increase the kinetic energy of the electrons which are incident, in that case what you can do, that your lambda can be as small as possible. Once your lambda is small, then the optical resolution, that will be small in this case. So you don't need to have, if it is 200 nanometers, that's why we can obtain the nanometers. Let's say that we can also probe like 2 nanometer with the help of the scanning electron microscope. So that is the advantage in this case. So I hope that this concept is clear, that why do we need to have an electron microscope over and over this optical microscope in this case. So the next point which we would like to come, so if you come to this, we have answered the second question, and now we would like to come to the third question, which is the instrumental details in this case. So let's come one by one, what type of instrument it is. So I would like to draw it briefly. So the instrument details, no? So we are coming to the third topic, which is instrument details, no? So what will happen in this case, that you would have an electron source. Let's see that this type of the chamber we have. So we have this type of chamber, and in this type of chamber we would have all the details which are responsible in this case. So the first would be that here you would have the first lens, and then here you would have the second condenser lens. So let me make it a bit clear by doing this one, this one, this one, and then this one. So then here you would have the third one, which would be like this, and then you would have this. Let me extend it to a bit further so that we have more space. So what will happen, that initially you would have this is a chamber, and this chamber is the vacuum chamber. So what you would have, you need to have the vacuum in this chamber, vacuum chamber. And from here what will happen, that here you would have the electron gun, and this electron gun that will give you the electrons, no? And these electrons, they will be coming from here to here, and then they will be hitting onto the surface of the sample in this case. So here you have, this is S is the sample, okay, this is the electron beam, this is the electron beam which is there, okay. So what I can do, that this is the electron beam, and here you would have, this would be your the first condenser lens, and then here you would have the second condenser lens. This one is the second condenser lens, and then this is the objective, no? This is the objective. So if you look into this setup in detail, you have three main components. Now let me write them down. What are the three main components in this case that we have to highlight? In an electron microscope, you need to have the first component, which is the electron gun, no? Electron gun. Okay. In the second case, what you need to have the optics, or you will say that you need to have lenses, no? Lenses. And the third thing which you need to have a sample, which of course the electron will hit the sample through the lenses, and then what will happen, the scattered electrons, they will be detected with the help of the detector. So you would have these four important components in this case. So what will happen, the electron gun that will emit the electrons, and lenses, these are the electron gun. If you recall, it would be like a tungsten filament, no? Tungsten filament, no? Filament. So with the help of the, what will happen in case of the electron gun, that if you have a filament like this, then if you apply a particular bias to this filament, in that case what will happen, there will be the emission of the electrons from here, no? Because this material, that tungsten filament, is basically a low work function material which can emit the electrons in this case. So low work function, what is work function? Work function is the amount of energy which is required to knock out one electron from the metal surface. So if you knock out one electron, then that will be the work function. So lower the work function, higher will be the probability of the emission of the electrons in this case. And the second term which we would like to understand from here, so that would be bit clear, that these lenses, we remember that in the case of the optical microscope, we have the lenses like the optical lenses, but in case of the electron microscope, you have the electromagnetic lenses, no? Electromagnetic lenses. So what type of the lenses these are? Basically, you would have the electromagnets which will be deflecting the path of the incident electron beam in this case. So we have to make a distinction. Lenses does not mean that, okay, we are talking about the optical lens. These are the electromagnetic lenses. So in the presence of the optical, these lenses, what will happen? Your sample will be eliminated, and then you would have the detectors. Let me again recall what we are talking about. So if you recall this, so we have, again, this is the electron source from where we are having the electrons emitted, and these electrons, they will be focused with the help of these first condenser lens and second condenser lens, and then they will be coming onto the surface of the sample. Is it clear? So what will happen here, that now you would have the backscattered electrons, then you would have the secondary electrons, then you would have a detector over here, then you would have again a detector over here. second detector, which will be this will be for secondary electrons, this is for characteristic X-rays, okay? And this is for the BSE, that is BSE, which is backscattered electrons. So that this process, and most of what are the secondary electrons, what are characteristic X-rays, and how they are emitted, and what would be the backscattered electrons, what would be the probability to detect the images of this sample, that we would like to take in our next lecture. And if you come to the references, let me come to the references, what type of the references I have used. Reference books. So a lot of information is available there, okay? So the one of the book is CP Pule. So it is available free, okay? CP Pule nanotechnology. And then you have the Crandall's book, and then maybe on the internet, this is also on the nanotechnology. And that would be the end of this lecture. Thank you very much.